Okay, let's move to the diode models. So this basically covers the diode models part. Diode models. So during this previous discussion, we basically discussed about the characteristic curves of the diode. So this is the voltage and this is the current. So we found that the diode characteristic would be something like this. So this is actually Vk, the knee voltage. This is peak inverse voltage. So we identify that this is the forward bias region and this is the reverse bias region. So the forward bias region, so we identify that the voltage drop across the diode should be greater than or equals to Vk. So then we can observe a kind of a diode current, and once it becomes to the reverse bias region, so the voltage is simply less than Vk. So or else we can simply say that we uh, less than 0 plus V in between 0 and Vk. So, so in general we can simply say that the applied voltage across the diode is less than Vk. You can't see any diode current. ID 0 and this is reverse bias. So as a conclusion, V greater than or equals Vk, that is forward bias. V less than Vk, that is reverse bias. So these are the two conditions which we need to check whether the diode is forward bias or reverse bias. If the diode voltage or the voltage across the diode is greater than or equals to knee voltage or the barrier voltage, we can simply claim that it's in forward bias region. If it is not, like, we can simply claim that the diode is reverse bias region. So in the previous video we basically discussed like we can simply model this curve using Shockley equation. So it's a kind of an exponential type of a function. So if you need to analyze the circuit very precisely, we can go with the Shockley model. Otherwise we don't need to go for that precision. So we can approximate this behavior of vi characteristic with different type of simple approximation, and we can build a diode models based on these characteristic curves. So so the so we can do like this. So let's assume a scenario where so we simply assume that the knee voltage is 0. So knee voltage is 0. So let's assume there won't be any effect of knee voltage. So we can simply say that knee voltage is 0. So that particular case, diode characteristic would be something like that. So the knee voltage is 0. So then we can claim that if the voltage across the diode is greater than or equal to 0, so then the diode is in forward bias region. If this is less than 0, that is in reverse bias region. So these are very simple arguments or logics. So if the voltage across the diode is greater than 0, we can simply claim that the diode is in forward bias region, otherwise the diode is in reverse bias region. So by looking at these two conditions, so we can build a model like this. So the model is something like that. So this is the VI characteristic of this model. So if the voltage across the diode is greater than or equal to 0, you can see a kind of a diode current. If the voltage is less than 0, you don't see any current, ID equals 0. So by looking at this VI characteristic, we can simply claim that the applied voltage is less than 0. So you don't see any current, the current is 0. If the voltage is greater than 0 or equal to 0, you can see a kind of a diode current. So this particular model is identified as a ideal model. So in the ideal model, this is the characteristic curve. So this is the VI characteristic. It's something like a very simple switch. So it's a kind of a switch. So once you apply a voltage, the switch is on. So once you apply voltage, switch is on. Once you apply negative voltage, switch is off. So this is the ideal model. So this is basically equivalent to a switch. Once you apply a voltage, so you can see a kind of that current flow through the circuit. So if you apply a negative voltage, so then you don't see any kind of a direct current, so it's a kind of a open circuit. So how do you model this one? So this is the VI characteristic of the ideal model. So we can simply identify the regions. If the voltage is greater than or equal to 0, the diode is in forward bias region. If the applied voltage is less than 0, diode is in reverse bias region. Once it is forward bias, so then there is a kind of diode current flow through the device. So we can simply replace this diode using a short circuit element, because it's kind of a on state of the switch. So if it is reverse bias, you don't see any current flow through the network, so you can simply replace the diode with a kind of a open circuit element, which is equivalent to a kind of a off state of the switch. It's equals to off state of the switch. So in the first model, so which is actually the ideal model, ideal model. So ideal model, this is the characteristic VI characteristic of the ideal model. So then we can identify the regions based on this. If the voltage across the diode is greater than or equal to 0, we can recognize that diode is in forward bias region. If the voltage is negative or less than 0, we can identify it as it is in reverse bias region. So if the diode is in forward bias region, we can simply replace this diode with this short circuit element, because we know that with the characteristic curve, once you apply positive voltage, so the diode becomes conductive. So then there's a current flow through this one, so we can assume that this diode is working as a kind of a switch which is in on state. Similarly, if you apply a negative voltage, we know that there won't be any current flow through the diode based on the characteristic curve. So we can claim that this diode is act as a kind of a switch which is now in off state, So as a summary, we can simply say that for ideal model, so the ideal model, we basically ignore the barrier volt effect of this barrier voltage. So we basically ignore this one, this Vk is latent to B0. The characteristic curve is something like that. Vni. So then the when the applied voltage is greater than or equal to 0, we recognize that that is in forward bias direction, and that can be replaced with the short circuit element. and voltage is less than 0, we identify that diode is in reverse bias direction, and that can be replaced with in an open circuit element. So this is the on state of the switch, and this is the off state of the switch. So this is a very simple model. So if you are dealing with the circuits and if you want to apply this ideal model, so you need to clearly mention that you are assuming that ideal model. So you are assuming that the diode is an ideal diode. So without that assumption, you cannot apply these theories or concepts and simplify the circuit. So without this assumption, so whatever the calculation you made later on is completely invalid. So keep in mind, if you are using or if you are sticking to the ideal model, you have to clearly mention that the diodes are assumed to be ideal. Otherwise, whatever the calculation you do afterward is completely illogical. Okay, so this is the ideal model. So next we move to the so the again, like this is the characteristic curve. So initially we start with this kind of a characteristic, and come up with the ideal model. So then we can again take this. So here we simply ignore the effect of this new voltage. So we can take this, the effect of Vk as well. So once you include this Vk for this ideal model, so this characteristic would be something like that. So it's something like that. So now this becomes Vk, and this is the ideal model. Sorry, not ideal, this is actually simplified model. So in that simplified model, we simply bring this Vk also into the account, so the barrier voltage, and modify this ideal model slightly, and uh, consider the barrier voltage also as a kind of a decision making parameter. So for this case, we had two conditions. But what happens to this case? So for this model, so we know that this original characteristic curve is shifted by Vk. So then we can simply identify these two conditions. If the applied voltage is greater than or equals to Vk, we can claim that diode is in forward bias region. If the voltage is less than Vk, we can simply identify that the diode is in reverse bias region. So by looking at this characteristic curve, this diode is forward bias, you can observe kind of a current when the applied voltage is greater than Vk. So otherwise the current flow through the network is simply zero. So then we can simply identify that if the diode is forward bias, then the applied voltage should be greater than or equals to the knee voltage. So otherwise you can claim that the diode is in reverse bias direction. So if the so for this case you can identify there is a diode current. So it's non-zero diode current, and the voltage drop across the diode, so the drop across the diode is equals to Vk. For this case, if it is reverse bias, you can't see any current flow through the network, then this ID is actually 0. So how do you model the diode then for these two scenarios? So definitely if it is a reverse bias, you can simply say that no current flow through the diode, so we can simply replace the diode with the open circuit model. Nothing happened, nothing different than the previous. So the diode is reverse bias, so there won't be any current flow through the network. We can simply replace this diode using a show open circuit element. What about this case? So if it is forward bias, so there's a current flow through the network, and but again, once the current, while this flow current is flowing, it maintain a kind of a fixed DC voltage of Vk. So then ideally this particular diode can be replaced like this. So now this is the diode, this is the diode, and this is actually ideal diode. So in the simplified version, you have a fixed DC source of Vk. This Vk is the knee voltage or the barrier voltage, and a series ideal diode. So we have an ideal diode here and a series voltage source of value Vk. So this entire block represents the actual diode which we are looking for. So see what happens. So we can check whether these conditions are satisfying. So if it is an ideal diode, we know that the voltage drop across its terminal should be greater than or equals to 0 to make it forward bias. Okay, so if it is an ideal diode, so we know that the voltage drop across its terminal should be greater than or equals to 0 for make it forward bias. So if it is a forward bias diode, if this becomes forward bias, so it means like you can see a kind of a current flow through the network. So there should be a current flow through the network ID. At the same time, it should maintain a voltage of Vk. So to make this current flow through the network, definitely this ideal diode should be forward bias. It means like we have to maintain a zero voltage drop, at least zero voltage drop across these two terminals. Let's assume the value of this ideal diode is V0. So the voltage drop across this ideal diode is V0. So then this is actually this entire drop is Vd, that drop, or V, let's assume V. So V should be equals to Vk plus V0. V is the entire voltage drop across this diode, or the actual voltage drop across this diode, and Vk is the new voltage, and V0 is the voltage drop across the ideal diode. So this is the voltage drop, voltage across the ideal diode. So to make this entire block conductive, so this ideal diode should be forward bias. So from this we can identify the voltage across the ideal diode should be equals to V minus Vk. So to make this ideal diode forward bias, we should maintain this condition. See, so we should maintain this condition. So once we apply this one, we can simply that V should be greater than or equals to Vk. So V minus Vk. So if you want to have another step, So V minus Vk should be greater than or equal to 0, then V should be greater than or equal to Vk. So to make this ideal diode conductive, you have to maintain this. The applied voltage across this entire block should be greater than or equals to Vk. So then, so this is satisfied. So for the simplified model, this is the VI characteristic, and these two are the conditions you need to check whether the diode is forward or reverse. If the applied voltage is greater than or equals to the new voltage Vk, you can simply claim that it's in forward bias region. If the voltage is less than 0, you can claim that the diode is in reverse bias region. If the diode is reverse bias, you can simply replace the diode with the open circuit model. If the diode is forward bias, you can simply replace the diode with a DC source, because like we know that for the forward bias scenario, this diode gets this ideal diode gets conductive, and this ideal diode gets conductive mean we can replace the ideal diode with short circuit element. So then the volt diode would be something like that. So now the diode becomes a kind of a DC source of having Vk. Okay, so if the diode is forward bias, once you apply the simplified model, you can simply replace the diode with a fixed DC source of value Vk. If it is reverse bias, you can simply replace the diode with the open circuit model. So as a summary, we can simply claim these two. If the voltage across the diode is greater than Vk, diode is forward bias and can be replaced using this kind of a fixed DC source of value Vk. If the voltage is less than Vk, so diode is in reverse bias mode, and we can simply replace the diode with open circuit model. So this is the way we can model the diode when it comes to the simplified diode model. So these are the two conditions you need to satisfy. If you want to make it forward bias, whatever the voltage applied across the diode should be greater than or equals to Vk. So then if it is in forward bias region, you can replace the diode, with a fixed DC source of Vk like this. Keep in mind the polarities are like this. And if it is reverse bias, the applied voltage is less than Vk, and you can simply replace the real diode with the open circuit model. So this is the second model which we need to discuss here. So the third is again, so so in those two cases we didn't capture the curvature of the circuit. So this curvature is not captured anymore. So we can capture this curvature because we know that this curvature is exactly matching with the exponential curve. But the whole idea of modeling this data to make it very simple. So rather we modeling this as exponential, we can model this as a kind of a linear trend. So it's something like that. Okay, so then this trend actually represent a kind of a resistor. So this is V, this is I. So once you combine this is something like that. So we have this kind of a characteristic and this kind of character. So we have two models. Up to this, we can model this as a kind of a simplified model, using simplified model. So once this V goes beyond this Vk, we can model this as a kind of a we can include the resistor also into the circuit, because the trend afterwards, this Vk is almost linear. The Vi trend is almost linear. So the Vi trend is almost linear means we can simply represent this linearity using a resistor. So the third one is actually called piecewise linear. Piecewise linear model means like we have to uh, make it pieces. Like this is the one piece, so this is the second piece. So then, so the conditions for this piecewise linear also same, should be greater than Vk plus Vr, and if it is less than Vk plus Vr, this is reverse bias, so this is forward bias, so this is simply replaced using this. So the characteristic curve is something like that. So this is Vk. So up to this we have Vk. So after that the drop is simply the voltage drop across the resistor. So then to make it forward bias, we have to maintain a kind of the applied voltage should be greater than or equals to Vk plus the voltage across the resistance. Because we, so similarly you can replace like this. So then the diode can be modeled like this: plus minus, this is Vk, so this is R, this is the ideal diode. Okay, so this entire block is now representing the diode. This entire block is representing the diode. So similarly we can assume that to make this ideal diode forward bias, so we have to maintain a zero, at least zero voltage drop across these two terminals. So then, so we'll apply Kirchhoff voltage law. Then this V is the voltage drop across this entire block, which is the actual voltage appear across the diode, should be equals to Vk plus. So if it is, let's assume like Vr plus V out. So then to make it ideal, so there should be, so then ideal means this, to make it forward bias mean there should be a current flow through this network. So then once it is forward bias, this diode can be replaced using this short circuit element. So then there won't be any drop across this one, but there's a current flow through the network. So then this diode drop is actually V equals Vk plus actually id into R, so which is actually Vr. So to make it a forward bias, so from here we can simply say that V out equals V minus Vk plus Vr. So to make 0, V should be greater than or equal to Vk plus Vr. So then only this ideal diode get forward bias. So then in the piecewise linear model, so this is the Vi characteristic, and these are the two conditions you need to check whether the diode is in forward bias or reverse bias. If the diode is forward bias, you can replace the diode with a fixed DC source of Vk plus a series resistor R. This R is basically representing the gradient of this block. Okay, so this gradient of this curve characteristic curve represent the resistance of this one. So we basically are approximate this exponential trend to the linear trend, so and replace this linear trend by using a resistor. So if it is less than this amount, so then the diode is in reverse bias region, and we can simply replace the open circuit diode using open circuit model. So so this is very this piecewise linear model is very rarely used. Like we can stick into these first two models. So the first one is the ideal model. So second one is the simplified model. So if it is ideal model, so you have to make it clear this assumption should be there in the first row of the calculation. So without that assumption, whether you are sticking to the ideal or simplified, the rest of the calculation should be useless. Keep in mind all the time, either if it is given in the question, if not, you have to clearly mention that you are sticking to the ideal model or simplified model. So without having this assumption, initially the rest of the calculation doesn't make any sense. So if it is ideal model, we know that we can check the condition of the diode using this. If this voltage is greater than the new voltage, it's forward bias. Sorry, I made a mistake. If it is 0, forward bias, less than 0, reverse bias. If it is forward bias, we can simply replace it using a short circuit element. So you can replace the diode using short circuit element. If it is reverse bias, you can simply replace with open circuit element. If it is a simplified model, so this is the condition you have to check. If this applied voltage across the diode is greater than or equals to Vk, so it's simply forward bias, otherwise it's reverse bias. So if the diode is forward bias in the simplified model, we can replace the diode using a fixed DC voltage source of the value of Vk. This is the knee voltage or the barrier voltage. If it is reverse bias, you can simply replace it with open circuit element. So keep in mind, so we can, so for example, if you have a circuit like this, so you have resistor, diode and the source, so then we can simply model this circuit, or we can simplify this model circuit by replacing the diode by assuming either ideal model or simplified model. For example, if it is ideal model, you can assume that this diode is a kind of an ideal diode. So then you can evaluate the voltage drop across the diode and see whether it's greater than or equal to 0 or not. If it is 0, you can replace this diode with a short circuit element. If it is not, you can replace the diode with open circuit element, and then you can simplify the entire circuit to a circuit where you have resistors and sources only. So if you have diode, either you replace it with the open circuit element or short circuit element. If it is a simplified model, you can simply replace the diode with a fixed DC source of Vk or open circuit model. So then the entire circuit which you have this multiple diodes can be converted into a circuit where you don't have diodes. So then the whatever the circuit you obtain after simplification is just the sources and the resistors only. So likewise, you can simplify the circuit containing diodes to a circuit where you don't have diodes and only the components in the diode would be resistors and the sources. So then you know that how to treat or how to analyze the circuit where you have fixed DC sources and the resistors. So then you can apply Kirchhoff voltage law, Kirchhoff current law, nodal analysis, mesh analysis, divider rules, and any kind of circuit theory to obtain the currents and voltages in the particular path or branch or across any element. So later then you can apply whatever the circuit theories and analyze the circuit. But if you have diodes, first you have to stick into the model, then replace the diode with appropriate element, whether it's forward or reverse, depending on the forward or reverse. So then you can do the analysis. So we'll do the couple of examples in the later video. So for the moment, so we are basically using ideal and simplified model for the latter part of the analysis. We uh, at the moment we'll simply avoid this applying piecewise linear model, but if you want to make it more precise, you can go for piecewise linear, or we can stick into this Shockley model. So otherwise we can align with the ideal model or simplified model. So those two models give a kind of a reasonable insight or a kind of a reasonable justification or explanation about the behavior of the circuit, and whatever the values we can calculate from these two models may be very close to the real voltages and current. So in analog electronics, the whatever the values we obtain by approximating this to the ideal or simplified model would be more than enough to explain the behavior or analyze this circuit.